So this is going to be a very quick intro to a little bit about PFAS forensics. So, okay. So this slide kind of gives you the big picture summary of the different signatures we may see, which can reflect different sources and our different fate and transport scenarios. So at the top of the slide, you see like an aqueous film forming foam source with more of the red-orange perfluorosulfonic acid. And down here at the bottom, you see more of a plastic source with more of the blue perfluorocarboxylic acids. And these types of chemical signatures can be used to identify various characteristics, and not just of sources, but also characteristics of different fate and transport scenarios, like the breakdown of telomers, like 6,2-fluorotelomere sulfonate further downstream in a plume. And we can show a plume becoming more enriched in something else because of the breakdown of these precursors. And there can also be a change in signatures, due to commingling of sources, causing differences in pie charts along the length of a plume. So, this slide here is just going to kind of highlight some of the unique characteristics of different products or different industries. So some of the PFAS that are typically associated with the paper packaging industry are listed here: the side chain fluoropolymers, N-ethyl perfluorooctane sulfonamide acetic acid, N-ethyl fosa. This is a polyfluorinated compound, a precursor, and it's a breakdown of N-ethyl perfluorooctane sulfonamide ethanol, N-ethyl fos. And we'll also see short chain perfluorocarboxylic acids and perfluorosulfonic acids associated with the breakdown of N-ethyl fosa. In the textile and leather industry, we'll see polymers, PFOA, and fluorotelomere alcohols. And the polymers can break down to PFOA and other perfluorocarboxylic acids for the most part. And the perfluorocarboxylic acids are likely what we'll see on the signatures. The fluorotelomere alcohols don't really last very long. These are the more volatile PFAS, and they're typically identified as intermediates. However, under some anaerobic conditions, they can last longer. The next one, AFFF, I'm not going to spend time on it on this slide, but I'm going to get into a little bit more detail on the AFFF components in a minute. This is a really important one because it's a major source of PFAS contamination. The wastewater treatment plants and landfills. So 5,3-fluorotelomere carboxylic acid, these are common in landfill leachate. There's papers out there saying it's a good marker compound for landfills due to carpeting. However, we are finding that 5,3-fluorotelomere carboxylic acid also shows up in the breakdown of other telomers that are not polymers. So like the 8,2-fluorotelomere sulfonate. It's actually like almost always identified, so it's really no longer a great marker compound for landfills. And sometimes it's actually hard to state what the common components of wastewater treatment plants and landfills would be, because it's very dependent on the sources feeding the wastewater treatment plant or landfill. And then for metal plating. So the metal plating industry was allowed to use PFOS in the United States until about 2012, and that's 10 years past the date it was phased out in the United States, before they actually went to the replacement fluorotelomere sulfonates. So it's mostly used for chromium plating to prevent splattering of hexavalent chromium. And EPA allowed PFOS in this industry longer because the risks of PFOS are much less than the risks of hexavalent chromium splattering. The F53B that's listed here is a replacement for PFOS as a mist suppressant in the metal plating industry. And from what I know, I think it's pretty much only been used in China. But this particular replacement compound is now interestingly included on the EPA 537 analytical method list of compounds. So all AFFF contains PFAS, both historically and those being sold today. So if you or your client have foam in stock or are purchasing new foam that's labeled as AFFF, it definitely contains PFAS. And there's generally 3 categories of AFFF. So first is the legacy first generation AFFF. So 80% of these were PFOS-based foams sold under the brand name 3M Lightwater. 20% or 8,2-fluorotelomere sulfonate base sold by other companies, not 3M. And sales ended about 2002, but many locations may still contain this in their inventory. And these foams typically contain PFOS, perfluorohexane sulfonic acid, and maybe even PFOA. And some of the early AFFF from the 1960s to early 1970 was also PFOA based, PFOA based. Second is the legacy second generation AFFF. They were sold from about the 1970s to about 2016. So these foams can be fluorotelmer based or PFAS derivative based. So not PFOS, but derivatives of PFOS, which can ultimately break down to PFOS. And these foams can contain long chain fluorotelmers, which are those polyfluorinated precursors that can break down to PFOS. And third is the modern fluoropolymer AFFF. So most foam manufacturers have now transitioned over to the use of only short chain with C6 fluorotelmers. These foams do not contain or break down to PFOS, and they're made with only short chain fluorotelmers. They may contain trace quantities of PFOA as a byproduct of the manufacturing process, but PFOA is not an ingredient of these foams. So it's a lot of information, but it's important to know that we can differentiate these different types of AFFF. So here you can see some different AFFF signatures. The first one is the first generation legacy PFOS-based AFFF, which also contains a good percentage of perfluorohexane sulfonic acid. And actually, some of the different lots of AFFF produced by 3M had different ratios of PFOS to perfluorohexane sulfonic acid. The second one here is a second generation AFFF. So this one has equal amounts of 6,2 and 8,2 fluorotelmer sulfonate, a little PFAS, and also a little PFOA, which is from the breakdown of the 8,2 fluorotelmer sulfonate. And products in this AFFF, so either the 6,2 or 8,2 fluorotelmer sulfonate derivatives will break down to the actual fluorotelmer sulfonate, and that breaks down to the perfluorocarboxylic acid that you see in the blue part of the pie chart. And then the last one is the modern fluorotelmer AFFF, the one most foam manufacturers have switched over to, with the major component being 6,2 FTS derivatives, which can break down to 6,2 fluorotelmer sulfonate. So this is an actual water sample from a release at an airport, and it was sampled 2 days after the release from the catch basin, and a lot of the pure foam had flushed out by the time it was sampled. So the release was believed to be a modern C6 fluorotelmer-based AFFF. But you can also see here some PFOS was present. And this was actually determined to be likely contamination from C8 foam that was in the system when they changed out their system from C8 to C6 foam. Something that airports or really any industry needs to be very careful with. So the system was not really decontaminated properly prior to switching over to the C6 foam. Anyways, the original PFAS analysis of this sample showed a total PFAS concentration of 100,000 nanograms per liter. You can see here at the top. So we did a top assay analysis on the sample, and the top assay takes the original sample, does a very strong oxidation of it to break down any polyfluorinated precursor compounds. So the top assay will not break down PFOS, will only break down polyfluorinated precursors. So after the oxidation, the sample is again analyzed for the regular list of PFAS compounds. And you can see here at the top that the total PFAS concentration after that oxidation is an order of magnitude higher, about 1 million nanograms per liter. So let's look at the bottom part of the slide now. So you can see the 6,2 fluorotelmer sulfonate, which is a polyfluorinated precursor, was oxidized because it reduced in concentration, went from 40,000 nanograms per liter to 1,000 nanograms per liter, while many of the perfluorocarboxylic acids, the light blue here on the pie charts, increased in concentration. So you see a dramatic increase in concentrations for the C4, C5, and C7 perfluorocarboxylic acids here. So something else is breaking down besides just the 6,2 fluorotelmer sulfonate that we're not analyzing for, that's coming out as these C4, C5, and C7 carboxylates. And it's likely 6,2 fluorotelmer sulfonate with various derivatives. It may not be 6,2 fluorotelmer sulfonate itself, but derivatives of that compound. Also, it's expected the PFAS concentration did not really change. It did go up a little bit, but it just may be within the acceptable degree of analytical measurement error. But an important observation here is that even if you use a 36 compound PFAS list, you're going to see 100,000 nanograms per liter of total PFAS. when the true concentration of fluorinated compounds in this sample is closer to 1 million. So that really needs to be taken into consideration when you're designing treatment systems, but it's also very useful for forensics in seeing what else may be in our sample. So this is a catch basin sample from a Teflon coated fiberglass manufacturer. And it has an obvious signature. It's very distinct from the AFFF signatures that we just looked at. And it's just an example, of the uniqueness of signatures in the manufacturing industry versus AFFF. I mentioned this earlier, but this signature is from an article showing 5,3-fluorotelmer carboxylic acid as dominant in the landfill leachate, and the article says it's coming from carpeting. It's a very unique signature here. I did mention earlier that 5,3-fluorotelmer carboxylic acid may have different sources. So it may be from the carpeting, but it also could be due to the breakdown of telomers. And so it's complicated, and I think it's easy to be misled by the 5,3-fluorotelmer carboxylic acid. And sources to landfills, again, will be a mixture of different ingredients to begin with. The effluent composition is obviously going to depend on the wastewater treatment plant contributions and also aerobic degradation of precursors, the polyfluorinated compounds. So this is the signature of effluent passing through a wastewater treatment plant from a chromium plating facility. The one shown here is likely from a processed wastewater system, not a POTW. The 6,2-fluorotelmer sulfonate would not exist if it was a POTW. But the bottom line here is that the signatures of wastewater treatment plant effluents can be highly variable depending on the sources feeding the plants. So I wanted to show you this. This is from a regional airport that we worked at. And at one airport, we were able to identify 5 different AFFF sources. So number one, the runway here, this was an emergency response in 1996. And this is in the area of the runway here at the top of the figure where foam was used. And you can see the signature going down from the runway through the creek to the lake are all pretty comparable. And this is 4 miles long, all one source, same signature, same relative concentration. So it was an old source, it was still persistent, and it impacted lakes and recreational ponds for 4 miles. Second, there was a nozzle training area. This eventually goes to the creek and to the lake. Third, on the top up here, this was a PFOA-rich source. So it was kind of an oddball. It's a different signature that we think may be associated with 8,2-fluorotelmer sulfonate, AFFF, not 100% sure. But it was small and it was like a low mass source. The fourth was a hanger release. This was from a new modern foam. It was barely detectable after 2 months and not a major constituent after 2 months. And the fifth one here, these 2 pie charts, these show another potential source from a release of concentrated AFFF. And they kind of look like the pie charts from the older emergency response here on the left, where there are differences between all these releases based on the ratio of PFOS to perfluorohexane sulfonic acid. So as I mentioned earlier, different lots of AFFF produced by 3M had different ratios of the PFOS to perfluorohexane sulfonic acid. So basically, using this forensics, we were able to save our client actually a lot of money by demonstrating which source of PFAS contamination was due to their AFFF. And this is my final slide. So as we know, the standard PFAS analyte list continues to change. And one of the problems is that the largest data set we currently have is UCMR3, and that only includes 6 perfluoroalkyl acids. So when you're looking at comparing signatures, you have to really think about, what the analyte list was. So we need to integrate the chemical data with the hydrogeological data and other forensics evaluations. There has to be a multiple lines of evidence approach. So this slide just shows you the same exact data set, but the evaluation looks really different based on the analyte selected. And you can see on the left, the pie charts, the top and bottom ones that are circled, looks like only PFOA. So you would think maybe it's a Teflon manufacturer. But the second set of pie charts on the right, these are the same 2 samples, okay, for the same pie charts for the same 2 samples, but with more analytes. And you see something completely different going on here. The signatures are very different. So the analytical list is very important for source identification. And that's all I have today. Just wanted to give a brief overview on some forensic tools.